Pluto's circle has consistently presented potential entanglements. Its way crosses that of another planet, which has raised worries since the earliest reference point. Pluto, a little and cryptic planet situated at the furthest reaches of our planetary group, has turned into a subject of huge interest in ongoing cosmic discussions. Late reports show a potential crash with Neptune, which has raised cautions within mainstream researchers and among space devotees. Notable researchers, for example, Neil deGrasse Tyson and Michio Kaku, have voiced their fears about the potential repercussions of such an event. But what drove Pluto to be on a collision course with Neptune, and what might this grandiose showdown mean for Earth? Join us as we dig into the subtleties of this expected cosmic conflict and explore why astronomers are worried about this strange infinite behavior. Once viewed as an undeniable planet, Pluto was subsequently renamed as a dwarf planet, mainly in light of the eccentricities in its orbit. Regardless of this downgrade, Pluto continues to intrigue and capture the imagination of cosmologists and space lovers alike. Late assertions from specialists like Neil deGrasse Tyson and Michio Kaku have suggested that Pluto's orbit could cross Neptune's, raising the chance of a dangerous impact with serious ramifications for our planet. Pluto's journey around the Sun is truly remarkable because of its surprising qualities. Its orbit is very lengthy, requiring a stunning 248 years to complete one full revolution. Since its discovery in 1930, Pluto has not yet completed a full orbit around the Sun. What makes Pluto significantly more intriguing is the highly elliptical shape of its orbit, which stands out strongly from the almost round orbits of the major planets. Moreover, Pluto's orbit is tilted at a 17 degrees angle relative to the ecliptic plane, resulting in a much more extreme path compared to the sphere of other planets. This combination of orbital inclination and elongated shape complicates Pluto's movement, making its orbit unique. An interesting feature of Pluto's orbit is that it repeatedly intersects Neptune's orbit at regular intervals. At these points, Pluto's path takes it closer to the Sun than Neptune, which defies our expectation of how the planets should be positioned in the solar system. Further investigation reveals that Pluto's orbit is far from a perfect circle. Rather, it follows an elliptical or oval shape, causing its distance from the Sun to fluctuate significantly. At its closest, Pluto comes within roughly 30 astronomical units, AU, of the Sun, but at its furthest, it stretches to over 49 Australian dollars, almost double Neptune's average distance from the Sun. Besides, Pluto's orbit is tilted at an angle relative to the other planets, further complicating its interactions with Neptune. This inclination is key to understanding how Pluto and Neptune interact when their orbits cross. The gravitational forces between the two bodies pull at each other, slowly altering their respective paths. This unique relationship highlights the interconnected nature of the solar system, where the gravitational pull from one planet can influence the motion of another. Thanks to advances in technology and improved observational tools, astronomers have been able to track Pluto's movement with increasing precision. This has allowed for a clearer understanding of its orbit and the potential effects it might have on the overall stability of the outer solar system. While the likelihood of a direct collision between Pluto and Neptune is low, the possibility is still actively studied, as the consequences of such a collision could be catastrophic. Despite Pluto's small size and its distant location, it continues to captivate scientists and space enthusiasts alike. A central question remains: why hasn't Pluto collided with Neptune by now? The answer lies in the gravitational influence of other planets. Since Pluto's discovery, astronomers have been trying to understand its peculiar orbit. Unlike most planets, which follow relatively stable paths along the ecliptic plane, Pluto's orbit is distinctive because of its steep angle and elliptical shape. The mystery deepened when it became clear that Pluto's orbit crosses Neptune's. Despite this apparent danger, Pluto's orbit has remained remarkably stable, demonstrating the complex forces at play within the inner solar system. The study of how Pluto, Neptune, and the Sun interact presents a significant challenge for astronomers. Predicting their movements requires a deep understanding of the gravitational forces that affect each other's paths. To help resolve this vast puzzle, scientists rely on several specific conditions, including ASMU libration, scope libration, VOP, and Steve's and Kaplan disconnection. For example, ASMU libration plays a crucial role in maintaining the stability of planetary orbits. When Pluto crosses Neptune's orbit, it stays at least 90 degrees away from Neptune, ensuring that a direct collision does not occur. Scope libration ensures that Pluto stays positioned above Neptune's path as it approaches, reducing the likelihood of a crash. The VSOP variation, named after researchers von Ziepel, Steves, and Kaplan, explains why Pluto's orbit appears unusual but remains stable over long periods. Even though space seems turbulent, there are hidden patterns that prevent Pluto from colliding with Neptune or drastically altering its orbit. The concept of orbital chaos describes how a celestial body's path is extremely sensitive to its initial position. Even minor changes in Pluto's starting position or speed can have significant effects over long periods. To model Pluto's interactions with Neptune and other bodies in space, scientists use advanced computational simulations. These simulations investigate the potential outcomes of even the smallest shifts in Pluto's trajectory. In the late 1980s, these simulations uncovered a fascinating result. Despite Pluto's seemingly stable orbit, it can still behave unpredictably. A slight change in Pluto's position or velocity could lead to dramatic shifts in its orbit over time. However, even with these uncertainties, Pluto's orbit has remained stable for billions of years, suggesting that despite its erratic motion, it follows an underlying order. The unpredictability of planetary orbits, such as Pluto's, makes it difficult to predict long-term changes with certainty. These models require highly accurate initial conditions, as even small errors in the data can lead to vastly different outcomes, making precise predictions very challenging. Understanding Pluto's orbit is especially important when considering a potential impact with Neptune. This information contributes to a broader understanding of how our solar system functions. Pluto's orbit serves as a case study of how orbits that seem chaotic can ultimately reach equilibrium, governed by gravitational forces and motion. It is essential that we continue to monitor and study these celestial dynamics to gain a clearer understanding of our place in the universe. Pluto's orbit offers a typical example of the erratic nature of space. Unlike the orbits of other planets, Pluto's path is highly elliptical, leading to unpredictable encounters with Neptune. This erratic motion makes it challenging to predict the long-term behavior of the system. However, gravitational forces play a key role in preventing Pluto and Neptune from colliding. Gravity, the force that pulls objects toward each other, ensures that, despite their overlapping orbits, the two bodies remain separated most of the time. These gravitational interactions demonstrate the delicate balance of forces that govern space. While a direct collision between Pluto and Neptune remains unlikely, such an event would have immense consequences for our understanding of the solar system. The release of energy from such an event would be colossal, and the debris scattered across space could have sweeping effects, potentially impacting other planets and moons. Neptune's orbit itself could be altered, further complicating the dynamics of the outer solar system. As space exploration continues to advance, Pluto's orbit serves as a reminder of the many uncertainties that still exist. Researchers continue to study Pluto's trajectory to better understand how large planets affect its movement. This knowledge is crucial for understanding the complex interactions between celestial bodies and what their movements might mean for each other. Despite the unusual nature of Pluto's orbit, some of the world's premier scientists, such as Neil deGrasse Tyson, have speculated that Pluto could eventually collide with Neptune. Tyson, a renowned astrophysicist, views Pluto's renaming as a dwarf planet as an important step and emphasizes the need for continued study. He believes that Pluto's eccentric orbit highlights the fact that much is still to be discovered about space and the forces that govern it. According to Tyson, the mysteries of space make studying it so compelling, and he encourages others to explore the fascinating intricacies of celestial mechanics. Tyson, along with other experts, expresses concern over the potential risks posed by Pluto's strange orbit. If a collision were to occur, it could have devastating consequences for the solar system. The release of energy from such a collision would be immense, and the debris spread throughout space might influence other planets and moons, potentially altering their orbits. Theoretical physicist Michio Kaku, known for his work in string theory, also offers valuable insights into space exploration. Kaku believes that studying phenomena like Pluto's orbit is essential for understanding the broader principles of celestial mechanics and theoretical physics. He suggests that studying Pluto's interactions with Neptune could help guide future space missions and improve safety in space exploration. Kaku also highlights the importance of understanding gravitational forces in the context of space exploration. Kaku's insights into the importance of understanding gravitational forces in space exploration underscore how crucial it is to study the dynamics of distant celestial bodies like Pluto and Neptune. He believes that these studies are not just about understanding one specific interaction, but about grasping the broader mechanics that govern the entire universe. This knowledge could be pivotal for the future of space exploration, particularly as humanity aims to venture further into the solar system and beyond. By understanding the gravitational influences that shape the orbits of planets, moons, and other celestial objects, scientists can better predict potential hazards and prepare for unforeseen cosmic events. For instance, understanding Pluto's orbit and its interaction with Neptune provides valuable information for predicting possible collisions in the future. Although the likelihood of such an event occurring is extremely low, the implications would be immense, not just for Pluto and Neptune, but for the entire solar system. In the long term, studying Pluto's orbit also helps scientists better understand the early formation of the solar system and the processes that shaped the planets. Pluto, as a leftover body from the early solar system, serves as a time capsule, offering clues to the past that could help unravel the mysteries of how our solar system came to be. This is one reason why Pluto remains such an intriguing object for astronomers and astrophysicists alike. Furthermore, Pluto's orbit is a test case for understanding celestial mechanics in extreme conditions. Its highly elliptical orbit, the tilt of its path, and its interactions with other bodies in the solar system provide an opportunity to test our theories about gravity and planetary motion. The study of Pluto's path also challenges existing models of planetary behavior and invites new theories and discoveries that could expand our understanding of the universe. Even though Pluto is now classified as a dwarf planet, its importance in the study of astronomy and planetary science cannot be overstated. The study of its orbit, its interactions with Neptune, and the forces at play within the outer reaches of the solar system continues to offer valuable insights. As new technologies and methods of observation continue to advance, it is likely that even more surprising discoveries about Pluto and its place in the cosmos will be made. In conclusion, the study of Pluto's orbit and its potential interactions with Neptune represents a fascinating chapter in the ongoing exploration of our solar system. While the possibility of a catastrophic collision remains a distant one, the study of these celestial bodies and their dynamic behavior is essential for deepening our understanding of the universe. With the continued efforts of scientists, theorists, and astronomers, we may one day uncover more about the forces that govern not just Pluto, but all the planets in our solar system, and beyond. As we continue to explore the depths of space, our understanding of Pluto and its interactions with Neptune could serve as a catalyst for future discoveries. While it may seem like a distant and isolated topic, the study of Pluto's orbit is intrinsically tied to the broader field of planetary science and astrophysics. Each new insight gained from studying this distant world could help us refine our understanding of the formation and evolution of our solar system. One area where Pluto's orbit is particularly valuable is in helping scientists predict the behavior of other distant objects in the solar system, such as trans-Neptunian objects, TNOs, and Kuiper belt objects, KBOs. The Kuiper belt, a region of icy bodies beyond Neptune, is populated with objects that share similar orbital characteristics with Pluto. By understanding the gravitational interactions between Pluto and Neptune, scientists can extend these insights to predict the movements and behaviors of other objects in this distant region of the solar system. Moreover, the study of Pluto and its orbit also holds potential for understanding the behavior of exoplanets in other star systems. Many exoplanets discovered outside our solar system have eccentric orbits, and studying how gravitational forces shape the orbits of bodies like Pluto and Neptune could provide insights into the dynamics of distant exoplanets. This knowledge could also help us better understand how other star systems evolve and how planetary systems form around stars in different environments. As space exploration advances, the tools and techniques for studying distant objects like Pluto are improving. Missions such as NASA's New Horizons, which flew past Pluto in 2015, have provided invaluable data that continue to shape our understanding of the dwarf planet. The data collected from these missions allows scientists to model Pluto's orbit with greater precision and refine their predictions about its future interactions with Neptune. This also opens the door for future missions that could gather even more detailed information about Pluto and other bodies in the outer solar system. The discovery of new celestial objects and the development of better observational techniques mean that our understanding of the outer solar system and of objects like Pluto will continue to evolve. As we learn more about Pluto's orbit, we may uncover new mysteries that challenge our current understanding of space and planetary dynamics. These discoveries could have far-reaching implications for everything from planetary formation to the search for life elsewhere in the universe. In essence, Pluto serves as a reminder of the complexities and mysteries of the universe. Despite being a small, distant world, its orbit has captured the curiosity and imagination of scientists and space enthusiasts alike. Its interactions with Neptune may hold the key to understanding the broader mechanics of the solar system, and possibly even the fundamental forces that govern celestial bodies throughout the cosmos. As our knowledge continues to expand, Pluto's role in the story of the solar system will remain an important and fascinating chapter in the ongoing exploration of the universe.